Good morning, everyone. It's great to see all of you. So I'm going to talk a bit about the part of Julia that I've been working on mostly for the past... oh, you can't hear me? I've got to get closer, right? OK. Just max it out.
Is that easy?
OK. How's that? OK, good. All right. So I was saying I'm going to talk about the part of Julia that I've been working on mostly for roughly the past year. What is the type system? What am I talking about here? So in Julia, we have these things that we call types, which is basically a grammar and vocabulary for answering what kind of thing is this? What kind of thing do I have? And then relatedly, the important thing it does is given two descriptions of kinds of things, could one be substituted for the other? So if I have an array of x's over here and I have a y, can I put that y in that array of x's? Is that a valid thing to do? So this is kind of a fundamental, important operation in a programming language. And the answer is called this idea of subtyping, where the answer to that is yes if y is a subtype of x, which is written like this. It uses this less than colon operator, which you will see quite a bit in Julia code and in this talk. And so this is the subtype relation, if you will. So this is used in many places in Julia. It's used to find applicable methods, for instance. So every time you call a function, we have the types of the arguments, and then we have to find a matching method where those argument types are a subtype of the method signature that the author of that method has written. And this also provides the kind of basic tools for analyzing programs and optimizing them. So this is actually distinct from all of the part of the language that generates code and does type inference, but this is sort of underneath all of it. So when we the type, I'm not actually going to talk really about type inference today, but when we do type inference, it's sort of manipulating these quantities. And kind of subjectively, many people feel that the type system that a language has is responsible in large part for sort of the feel and power, if you will, of the language in kind of in some very explicit ways and in some more intangible ways. So I'm going to really just talk about this aspect of Julia, which is really, it's kind of a small part of the system really, but it's a kind of interesting and important one. So I think one thing that's happening now is we've maybe been around long enough that we have some history, actually. So Michael was talking about back before we even had a version number. I didn't even go that far back here, but I'll give kind of briefly the history of the language from the perspective of this narrow slice of it. So I would describe basically the first few versions of Julia, I would basically summarize like that. That was the situation for quite a while. But I was looking through the history, and there was one bright spot in there, which is that in 0.2 we added the immutable types, which were very successful. So that was one nice thing that came pretty early. And then nothing much happened until version 0.4, where that was sort of the first release where we made an interesting change to this part of the system. So what happened was we have tuples in Julia, and a tuple is basically just a couple of values put together. And the type of the tuple is just the types of the values in it. So it's a very simple, commonly used kind of little container. So what we used to do, we had this kind of clever hack, if you will, of how we implemented these, where when you made a tuple, we just took the pointers to the values and we just put them together in a new object on the heap and just gave you that. So we didn't have to do anything at all with respect to its type. We didn't have to do anything with the type tag. We did that lazily, so that later, if somebody asked what is the type of that tuple, then at that point we would do that just by reading the types off the things inside it. So we didn't have to have a separate representation of the type of it. So at the time I thought that was, this seems pretty neat. I'll do this lazy trick. So that seemed kind of cool. But what happened was the immutable types and the more commonly used sort of struct-like types that you declare they started taking off, and they developed all of these great capabilities of having efficient memory layouts and being stored flattened into arrays, and they could do all these great things. And tuples kind of got left behind because I was using this hack which had that one kind of neat property, but it couldn't do all of those other things, and all those other things became way, way more important. So it became clear that we needed to stop using the special case for tuples and use the exact same machinery that all the other types were using. So we kind of brought tuples into that world in version 0.4. And that was kind of the first sort of type system related change and upgrade that we did. And then in 0.5 there was a little bit more. So Tim Holy actually added he put the n in vararg tn. So previously we only had the ability to match any number of things at the end of an argument list, and Tim Holy added the ability to have a parameter in there that could constrain how many things you'd match at the end of an argument list based on some parameter, which is a pretty neat, powerful feature. And this was kind of the first real and a kind of new fundamental capability in the type system that we got. And then also in 0.5, of course, we moved to this nominal function type approach to functions. But actually that, even with respect to this topic, that's even kind of a footnote because it didn't actually add any new types. It just kind of used them in a different way. But that was also kind of an interesting change there. But overall, the overall summary of this slide is that for these 5 versions, there were really minor changes to this. Now, not very much happened, actually. It's only, it's like two features in 5 versions, effectively, is what. So it's actually not a lot. I was even able to fit it all on one slide very easily, you see. So not really much happened. But in 0.6, that has changed. So in 0.6, we did a really serious overhaul. And there's all kinds of type system related stuff in 0.6, which I'm going to try to explain in the rest of this talk. All right, so why did we do this? Why did we need to do this in this version? So as of version 0.5, there were a couple kind of open questions about some fundamental aspects of the language. So if we have something like vector int, we know that's a vector of ints, we know what that is. But what if I left the int part of it off? What if I just said vector? What does that mean? So we know that that means any kind of vector. You can dispatch on that, and you've always been able to do that. But we didn't really have a good story about how does it work exactly. If I have, say, just the type vector, what if someone asked, well, what's the element type of that? Well, you can't say any because it's not a vector of any. It's a vector of an unknown element type. So how do we actually deal with that? How do we answer all the questions about that type? We didn't really have a clear answer. We didn't really know. And relatedly, you can write these method definitions that have these kind of extra parameters where, f, where there's some t, and it accepts a vector of t. Which sort of intuitively means you can take any kind of vector, and then inside the method I can see t is going to be the element type. But we didn't really have an explanation for what does that mean. What is that t doing in there? What kind of a thing is t? How does this method signature really work? We didn't really have a formal answer to that. So I think now we do. And the answer is related to this kind of subtyping that is sometimes called in the literature semantic subtyping, which means that types correspond to sets. So the less than colon subtype relation corresponds to a subset relation. And you can think of every type as being some set of possible values. So the any type, of course, is the universe of every possible value. And there's an empty type, which is the empty set. If you have int 32, that's the set of 32-bit integers. And then we can make these type unions, which of course does set union, and the correspondences are all pretty clear there. And then the way we decided that this should work for the types that have these sort of free variables in them is that those are actually an iterated union of sets. So when you have, so this is new syntax in 0.6. You can say vector t where t, and what that means is that is going to be a union of all types that could be written as vector t over all values of t. So it's like the union, but it's an iterated union. And so this kind of fits in with the overall set theoretic picture of the type system, and we thought about a few different options, and we worked through things, and we decided that this was kind of the thing that described best what the system was doing and that fit with how it works. So this is what we've settled on. So I'll tell you a bit about how they work. So basically what it lets you do is, given some type, if you don't know what one part of it is, you can take it out and replace it with a variable, and then wrap the whole thing in where that variable, and then you have something that represents that. So actually, if you look at the type just array, if you just take array by itself in Julia, this is actually its full structure. It's actually array tn, where t. So this is sort of the long-winded way to write it. So it still has array in there. So it's actually not really circular, obvious. So array does not really contain itself. In this other line, what is array is actually a different internal thing. Internally, it's represented by an object that we call a type name, but it's not something you usually ever use in a program directly. It's just kind of an internal thing because array only refers to this fully wrapped with where's type. The thing in there is just an internal thing that indicates you have some kind of array. And so here is how they work. So when you write array in your code, it's this. And now we're going to look at what happens when I try to instantiate this for particular parameter values. So this would correspond to having array, curly braces, float 32, 2. So I've just substituted that definition of array in there. And then this is how we will evaluate this. So the first thing that happens is the float 32, 2 is actually just a convenience feature for applying the parameters one by one. So it's equivalent to saying first do curly braces float 32 and then do 2. So it can be internally, it's just converted to that right away. And then we evaluate this in kind of a normal innermost first kind of evaluation order. Where the t, the where t part is kind of the outermost thing. So when you do something with this type, the t is kind of the thing that gets hit first, and it gets hit by the float 32. So float 32 goes into t, and you can see it gets substituted, and then the where goes away, and we have this. And then we do, the next step works exactly the same. The 2 goes in for the n, and then finally there are no wheres left, and we arrive at this at the final type. So this is how the process works. This is why when you look at these things, they seem to have kind of a weird backwards order where it's array tn, where t. The wheres kind of seem to happen in the backwards order of the way they're listed in the type, but this is why. This is why it works this way. And this example, of course, is really simple, but these things can get a lot more complicated. And as it gets more complicated, it can be important to know that this is what's going on and this is how it works. So there's some implications of this. So this explains now how our parametric types work pretty well. It can give pretty much a full account of how they work and what's going on. And the extra method parameters are the exact same thing. So in this signature, where I have f where t, where x is a vector of t, that's syntax sugar for writing the type of that method signature, which is, so the argument types in this case are going to be a tuple of vector t with a where t outside. So now we can just fully write out what the type of that method signature is, and you can write that anywhere and use it anywhere, not just in a method signature. And if you've ever used the type alias keyword, so that actually used to be how the vector type was defined. Vector was defined as an alias for array t1. And now we actually don't need the type alias keyword anymore because that's just another syntax for one of these where things. So that goes away, so that's nice. Another kind of issue that this solves is the where kind of indicates something about nesting order. So previously, if you wrote vector of vector, whoever writes that probably has some idea of what it means. But if you think about it, does it mean a vector of vectors where every vector inside is the same type? Or does it mean a vector of various different kinds of vectors? And that's kind of ambiguous. But so now we can distinguish those clearly. So this first one, vector t, where the where t is outside, that means you only get to pick one t for every vector in there. So this is a completely homogeneous vector of vectors. Whereas the other one, where the where t goes inside, that would mean you get a different t. You get a different element type for all of the internal vectors. So now we can clearly say which one we mean. And finally, because of the way this nesting and one parameter at a time style of application works, we can have variables with bounds that depend on outer variables, so which looks like this. So everything I've shown so far, the where t, the t is totally unconstrained. It could be any type, but you can also constrain it. So I could say array t where t is some subtype of real, which means all real arrays. And now we also have lower bounds as well. So we can say array t where t is at least int. What that basically means is an array which can hold ints. So if you want something that's possible to store an int into, you could write it like that, and then you'll know you'll be able to store an int in it. You might be able to store other things as well, but you'll definitely be able to store ints in it. So that would include array any and array real and so on also. And you can have upper and lower bounds. So I could say array t where t is between int and real. So no more than real, but at least int. And then finally, because of the way these nest, you can have them next. And this last one is actually quite useful. I think the last example here is sort of the most real-world kind of useful application, where I could say I have some array of A, where A is a kind of array of R, where R is some kind of real. So these things can now nest inside each other, which is, I think, something the folks working on linear algebra libraries have wanted for quite a while. So here's an example of something we could do. So here I have the default definition of eltype for arrays. So in previous versions, we needed two definitions to get this, actually. So we needed to say, if I have an abstract array of t type, then the element type is t. But if I have something else, I might have to try checking the supertype. So if I have some subtype of abstract array, that definition doesn't match. So try looking at the supertype and try to get the eltype of that as well. So which of course might not ultimately hit the abstract array case. So it doesn't really do exactly what we want, and it's kind of ugly that it takes two definitions. But now we can write it like this. So I can just say type t, where t is an abstract array is some subtype of an abstract array of e, where e, and then the answer is just e. So because of that nesting, we can now do this in a single definition, which is much nicer. Oops. All right, there is some syntax sugar to make it a little easier to write these things. So this was added by Steve Johnson. So you can say array just less than real, this prefix subtype operator, which expands to, it just makes up some variable name for you and expands that to array t, where t is subtype of real. And this only goes one set of curly braces outside. So that was what we decided was the way it should work. So if you have it nested inside, the where only goes out one level of curly braces. And syntax sugar number 2 is if you have a lot of variables, you have to write where over and over again. It gets kind of verbose. So we have a compact form where instead of writing where B, where A, you can just list the names. And in this case, so you put them between curly braces, and in this case, the kind of reversed order goes away, and you write them in the same order as they would sort of normally appear, which is a little bit confusing at first, but just I think this is still a good way to do it, because if you see the curly braces, then it's the forwards order. If you see wheres, then it's the backwards order. So you can write things like this, of where I just put the variables and bounds inside curly braces instead of having to write the two wheres. So you've both the syntaxes are available based on whatever looks nicer in your case. All right, so as part of introducing these union all or where types, we've had to extensively overhaul the subtyping algorithm, which is just a decision procedure that given two types, it says true or false, is one a subtype of the other. And that's a really hard problem, it turns out. So this is a really key operation for sorting methods, selecting methods, and it's used by type inference as well. So in this version, we have a totally new algorithm. I talked about it a bit at my last JuliaCon talk 2 years ago, where at that point we had basically a prototype. We had sort of the first barely working prototype of this new algorithm, and in the space of 2 years, we had improved that to the point where it can work on real-world Julia code, and now it is completely implemented in the system and in a released version. So that project is essentially done. So I'm very, it's very gratifying to see this thing actually ship after 2 years of thinking about it. The algorithm is basically based on a quantified SAT solver. So the structure of it is very similar to Boolean formula satisfiability with quantifiers. That's kind of how the algorithm works. So it's in the worst case, it's exponential time. So it can be bad. And in fact, there have been some regressions in package load times, which are often due to exactly this. So when we load precompiled packages, we have to incorporate its methods in the method tables that are in the system. So we have to do some resorting of them, which involves calling subtype. And actually, sometimes a package can take 10 seconds to load, and 99% of the time is just deciding subtype. So that has come up a few times. Fortunately, there are a lot of things we can do to put in fast paths to kind of try to handle common cases efficiently. But this particular algorithm there's still a couple little issues at the margins, but it seems pretty good. This one I think is pretty well understood. So I think we're doing pretty well here now. So here's some examples. These are actually the exact same examples from my talk 2 years ago, but now the only difference is they actually work in real Julia. So these are tuple types. In some cases, I've just dropped off the word tuple just to make it fit on the slide. But so you can do things like this. So if I have vector of integer and int, it knows that that's a strict subtype of vector ts, where t is some kind of integer and s is a subtype of t. So it can work out things like that. It knows that if you have pair of tt, that refers to a smaller set of possibilities than the same thing, but with separate variables, as you have more degrees of freedom. So that's a strictly larger type. And it knows that tuples and unions can distribute. So a tuple of unions is actually equal to a union of tuples. I'm not going to belabor this too much, but these things now all work. So there's, oh dear. So there are kind of there's some subtle cases. So this the type I mentioned before of the vector of vector t, where t you just change where the where nests in there. So those two versions of the type actually have nothing in common. One is not a subtype of the other. They're just really different types. Except, what if we made the bounds of the variable t equal, so that t was both greater than and less than int, for instance? Right? Well, then there's only one possible value of t. Right? T has to equal int in that case. So that means these things actually collapse, right? You don't need the t at all. You could just substitute int. And you can see if you substitute int for the t's here, the wheres go away, and there is no where anymore. So in that case, the types should be equal. And we actually get this right. So it is smart enough to know that if the bounds of the variables are equal, these types can actually be equal as well. So I'm proud of that. So here's a case that might come up. So if you write this definition in Julia 0.5, so f takes, the first argument is either a t or an array of t, and the second argument is an array of t. And we try calling it with 1 and the array of 2. And so that works. It can call that because it sees, OK, 1 is an int. So for the first argument, t equals int, because that was an int. And then the second argument, indeed, is also an array of int. So that checks out. It works. But if I try to call it with 2 arrays of int, it ought to work because that array case is in there. But it actually doesn't work because it sees the first argument, which is an array of int. So it says, OK, t is array of int. But now the second thing is not an array of int. So that does not match. So basically, it was using kind of a greedy approximation where it just finds the first convenient value to set for the variable, and it just picks that one and doesn't backtrack. So it didn't get this right. In 0.6, method matches. It does get it right. All right, so there's another key algorithm in this system, which is type intersection. Basically, given two types, finding another type that's a subtype of both. And this is used a little bit less in the system, but so where subtyping is needed kind of for method matching and for basically the soundness of type analysis. But intersection is what you need for precise type inference. Because what happens in type inference is the way you get good quality type information in inference is that you happen to know two things about the type of something, and you know that it's both, so you intersect them, and you now have a sharper type for what that thing might be. And so that is where we get a lot of the precision in type inference. So intersection is needed for that. And so far, this is a little bit less well understood than subtyping. We also have a totally new algorithm needed to handle the union all types. It works well enough to pass the test suite, I can tell you that much. But it is a little bit less well understood than subtyping. It needs more work. But there, I have this great example that I'm kind of proud of. So if you have two method signatures, t, pointer t, and then pointer s, s, they might seem at first to be very different. It's, oh, the first one is the case where the second one is a pointer, and the other one is a case where the first argument is a pointer. So those are different cases. But in fact, they have a non-empty intersection because as long as the t or the s is some type that's bigger than pointer, like any or something, then you could in fact have something that matches both of these. And the intersection is, this is actually what we are able to compute now for the intersection, and the answer is kind of surprising how complicated it is. But basically what happens is the t has to be bigger than pointer t, and then also you can do the variables in either order. So you need to try it both ways and then union together the results. So this was kind of a fancy. This is one of the motivating examples I was using. I figured, if I can get the algorithm to handle this, then it can probably do a lot of things. So we were able to get that working. So in summary, 0.6 I would say is kind of the first release where we know what everything is finally. And I think it's not likely that we'll do kind of another overhaul of this magnitude, because this design is it's pretty tightly constrained, and we have to kind of go with this, I think, now that we have it. Very quickly to talk about some categories of future improvements. So the things we need to work on in the future are the robustness of all of this, and some kind of data model improvements, which is sort of tangentially related to the type system, and then some possible actual type system features. So in the robustness category, so I haven't really said anything about method specificity. So specificity is used is the sort order, and it's very related to subtyping, but it's not quite the same thing. So it's also not fully understood. So that's something we'll work on formalizing. And the precision and correctness of subtyping and intersection. We have some examples of cases where it doesn't work or doesn't do what we want, and we'll be working through those. And we are always finding cases of things that people do that makes their package take a minute to load, where it's spending all the time in subtype, and where we can hopefully find some fast paths to avoid the exponential amount of work, where we'll keep doing that over time. Right, so specificity now works better because it can be based on subtyping, where we know if A is a subtype of B, but B is not a subtype of A. So in other words, A is a strict subtype, then it's more specific, that's fine. But that's not sufficient, because you can have cases like this, where you have some union types. The one on the left has int, and the one on the right has real, plus there's some other unrelated stuff in there. But clearly, if you had these two methods and you passed an int, you'd clearly want the one on the left to handle it, because it mentions int, whereas the other one doesn't mention that type. So there's some subtleties there around how specificity works, but I'm going to have to go quickly, unfortunately. So there's actually there's a research project going on about the Julia type system at Northeastern. So these intrepid folks have taken it on to try to understand Julia subtyping, try to reproduce our work and see if they can reproduce our algorithm and agree that it works, possibly even improve things about it, and try to publish a paper about our subtyping system. So these folks are working on it. I'm trying to collaborate with them. So hopefully a paper will come out of that, which would be great. All right, and possible future features. So one thing we have, there's a lot of work we can do is basically in the data model, which it's not exactly the same as the type system, but it's basically, at the end of the day, it's the things that the types are talking about, which is what kinds of data representations can we support in the language. So things like adding named tuples, variable size objects, and there's a whole bunch of things we can do there. I'm running out of time, so I won't belabor that too much. But another interesting possibility is to have complement and intersection types. So we could possibly be able to say, pick a method when some argument is not an array, for instance. And so these are, or we might be able to say something like, match the things which are iterable but not numbers if you don't like the fact that numbers are iterable. So these are kinds of types that I've shied away from because it seemed we can live without them clearly, and it seemed very complex to me to have unions and intersections and complements. So it seemed like a lot of complexity. I wanted to kind of avoid it. I thought it might even make the algorithm intractable potentially. So one thing that came out of talking with the Northeastern researchers is some of them are sort of the opinion that like, well, look, your subtyping is already so complicated, you might as well add these things. It's hard enough already. You might be able to add these. So it's possible that now types like this would be within our reach at some point in the future. Now we can at least contemplate it. And of course, the other big one, which I don't have that much to say about, but the other big missing piece, I think many people would agree, is some kind of protocols or trait types in Julia. So basically, the two big missing pieces are some way to characterize types by what they can do and not just by what they're called, basically. And then also to answer the question, if I want this thing to be a kind of array, what do I need to implement? So this is something the type system could help with. And there are basically two possible approaches. So one is the multiple inheritance approach, where you just explicitly declare what are all the things that my type can do. And so this actually would use potentially intersection types, because if I make a declaration like this, it means that this type is in the intersection of all of those things that it inherits from. So that's kind of a nice synergy. And then also we would have some just separate syntax for writing down the interfaces for these. And the interfaces would be kind of a separate feature outside the type system, but we could use it to check these. So this is kind of the straightforward version. It's pretty clear how to implement this, but it takes kind of a little bit more of a manual approach, because you have to explicitly declare which things you mean to implement. Whereas the other approach is to do some kind of protocol type, where you'd instead write down, say, here's the iterable type, and you write down what methods it consists of, this is a straw man syntax, but it would look something like this. And then what you do is, to see if something is a subtype of iterable, the type system would have to look to see if those methods exist. And so this makes me very, very nervous, because what you'd basically have to do this is you'd have some type, and you'd have to substitute it in here, and then go off and look for those methods, which involves doing subtyping of those signatures with the signatures that are out there. But then those subtyping queries could involve further queries of this kind, and so it seems to loop. And so this seems potentially too powerful and possibly undecidable. So I'm not sure we want to do this. But this has some nice properties too. This is kind of very automatic. If you happen to implement the right methods, then you get the type for free. So that's kind of a nice property. But we would still need then, if you mean to implement this protocol, but somehow you get it wrong, the system's not going to automatically tell you. It'll say, well, I didn't find the methods, so you're not iterable. So we'd still need a separate feature to say, well, I want to be iterable. What did I do wrong? So we'd still need yet more syntax for that. So kind of both designs have that feature where there's a kind of type level syntax, and then there's another syntax for talking about the intent to implement an interface. Where this decision is not fully made, we don't know what we're going to do, but this is probably a difficult enough problem that this is out of scope for version 1.0, which Stefan's going to talk more about, but this is probably like a 2.0 and future kind of a decision. We're not there yet. And that's it. I'm done.